In this question, we want to find all of the rational zeros of this polynomial. And part A is asking us to first list out all of the possible rational zeros. So to figure that out, what we're going to do is look at two numbers in this equation, the 45 and the 7. Factors of these numbers can help you figure out what all of the possible rational zeros are. So to start with, if we look at the number 45, I'm going to list out all the numbers that divide it. Those are plus or minus 1, 3, 5, 9, 15, and 45. There's quite a few. And I just put the plus or minus first. It's really plus or minus all of these numbers, but I just like to write it once. So I don't think that'll make much difference when we select our answers up here. Okay, next we look at the 7, and we write down all of the numbers that divide 7. Well, it's only two. It's plus or minus 1 and plus or minus 7. How do these factors help you figure out all the possible rational zeros? When we say a rational zero, what we mean is a fraction, some number a, an integer, divided by another one, b. These will be the numerators of our fraction, and these will be the denominators. And I'll just systematically go through. I'll divide 1, 3, 5, and so on by 1, and then I'll divide 1, 3, and so on by 7, and just write out all the possible fractions. So I'll just leave the plus or minus on the first term, but it's plus or minus 1 over 1, 3 over 1, 5 over 1. And so what I'm doing here is I'm taking these numbers and just dividing them by 1 to create a fraction. So we also get 9 over 1, 15 over 1, and 45 over 1. So these are possible rational zeros of the original equation. I'm now going to divide all these numbers by 7. So we could have a seventh, 3 sevenths, 5 sevenths, 9 sevenths, 15 sevenths, and 45 sevenths. This is the list of every possible rational zero of this original equation. They won't all work, probably 3 of them will. So let's see, is that A, B, C, or D? And it looks like it is A. So here they just put the plus or minus next to each number. Here I just put it in front. But that is good enough here. It's got to be choice A. On to part B for this problem. It now asks us to use synthetic division to test several possible rational zeros in order to identify one actual zero. This could take a long time, and that's why they suggest using synthetic division. But you can use long division too, and that will work as well. I'll actually go through using synthetic division. Now, I think on the last slide, I don't remember how long that list was, but there were a lot of rational zeros. I would actually recommend graphing the function at the beginning in Desmos to help narrow down what the actual zeros are. I did that already. I'm going to bring that graph in and I'll put it right here. So here it is. I took the original function, I put it in Desmos, and it gave me this equation. The reason to do this is it'll help narrow down what the actual rational zeros are. In fact, I can see that there are 3 rational zeros. There's one here, here, and here. We can choose any one of these for this part of the question and try dividing it into this polynomial. So, I think this one is exactly x is equal to positive 3. Was that number on our list? And it certainly was. There was a plus or minus 3 over 1 in part of our list, and so positive 3 is a number that would make sense. Let's verify this. I'm going to use synthetic division and divide that into this polynomial. So for synthetic division, it looks like this. You take the 0, which is 3. You then write down these coefficients in this order. So that's going to be 7, negative 5, negative 63, and positive 45. What we do is we first bring down this 7. I I then take this 7 and multiply to this 3, which gives me 21, and I'll put it right here. We then add these two numbers together to give us positive 16, and then we repeat this process. I then take 16, I multiply it to 3, it gives me 48. I then add these two numbers together, and that's going to be negative 15. I then take negative 15 multiplied by 3, and that gives me negative 45. I add those two numbers together, it gives me 0. And this number that we get at the end is the remainder. What this tells me is, if you start with a 7x cubed minus a 5x squared minus a 63x plus 45, which is a constant, the numbers that appear down here are going to be 1 less in the exponent. So this is really a 7x squared, a 16x, and then minus 15 as a constant with a remainder of 0. So this means we factored out x minus 3. Remember, this is the 0, and 3 makes this factor equal 0. And the thing that came out was 7x squared plus 16x minus 15. So, great. We have one of the zeros, and I know that because we had a remainder of 0. The final part of this problem for part C is to get the rest of the zeros. So we already know that 3 is a 0 because we used synthetic division to show that there was a remainder of 0. That meant we could factor the equation like this. So that takes care of this one here. But there are two others. There's one here, and there's one here. Now this one, it looks like it's negative 3. If we want to check this, we could use synthetic division and divide negative 3 into this original polynomial. But I think we can actually divide it into this thing here instead. It'll save us a little bit of time, and the process will be really similar. So here's what I'm going to do. My other 0 that we're testing is negative 3. That is certainly on our list from part A. I'm now going to list out these coefficients, which are 7, 16, and negative 15. Will this give me a remainder of 0? Step 1 is bring down the 7. I then take the 7 and I multiply it to this negative 3, and it gives me negative 21. When I add these two together, I get negative 5. I then repeat this process. Negative 5 times negative 3 is positive 15. And when I add those two things together, I get 0. What does this mean? It means I took my 7x squared plus 16x minus 15 and it reduced it to a 7x minus 5 with a remainder of 0. So in terms of factoring this thing, I didn't do anything to this x minus 3. I figured that part out in part B. But I just took this 0, divided it into this polynomial. So I factored out an x plus 3, and what came out was 7x minus 5. Great, so we can add negative 3 to the list. So let's see, I'll put that here. All right, so in part B, we got this positive 3. I even saw it on the graph, and I checked it with synthetic division. For part C, it looked like negative 3 also worked, so I tried it over here, and I got a remainder of 0. Excellent. But there is one more. There is some number right here that's going to be a 0 that I want to add to this list. Like, there's got to be something else. What is it? We can work backwards here. The positive 3 came from the factor of x minus 3, because if I put 3 here, it makes it 0. This negative 3 came from the factor of x plus 3, same idea. You put negative 3 here, it makes this 0. Well, wherever this factor is equal to 0 will correspond to this spot right here on the graph. What is it? It turns out it's really easy to solve that. You can take 7x minus 5, set it equal to 0, and solve for x. I will first, add 5 to both sides. That gives me 7x is equal to positive 5. I will divide both sides by 7, and I get my answer that x is equal to a positive 5/7. I can add that to my list. Now, that definitely corresponds for a number that's a little bit less than, well, this is 1, so it's a little bit less than 1, and it's at exactly 5/7. And this positive 5/7 was on the original list of numbers.